It's a stunning insight. Just as an ant might feel forces pulling it left and right as it walks over crumpled paper, when it's simply the shape of a surface dictating its path, Einstein saw that what we feel as the force of gravity is, in fact, the shape of the space-time we're moving through. Einstein now has everything he needs to formulate his final theory of gravity.
So the formula is really simple. G mu equals to
G for the shape of space-time, and T for the distribution of mass and energy.
So this very simple formula captures all of Einstein's general relativity. It's a beautiful, simple equation, but it's a lot of work to unpack the symbols, the mathematical symbols, and see how in this very simple formula, the whole geometry of the universe is hidden. It's kind of an acquired taste to see the beauty. It's also a signature formula for Einstein. The true mark of his genius is that he combines two elements that actually live in different universes. The left-hand side lives in the world of geometry, of mathematics. The right-hand side lives in the world of physics, of matter and movement. And so perhaps the most powerful ingredient of the equation is this very symbol equal sign here, these two lines that actually are connecting the two worlds. And it's quite appropriate, there are two lines, because it's two-way traffic. Matter tells space and time to curve. Space and time tells matter to move.
The general theory of relativity made predictions of things which look really strange. For example, the idea that light bends when it passes near a very heavy body. No one had ever looked for that. No one had ever observed it. Einstein was desperate to get astronomers to make that test.
Einstein's theory predicts that when light from a distant star travels close to the sun, the warped space around the sun bends the light's path. In May 1919, the English astronomer Arthur Eddington traveled to the African island of Principe to record images that would show this phenomenon.
What Eddington had been able to do was take photographs of stars during a total eclipse of the sun. So the moon blocked most of the brightness of the sun, and little pinpricks of light could be seen around the sun, otherwise would be lost in the glare. And Eddington and his colleagues were able to measure that the appearance of those stars had been shifted compared to where they would have been had that big mass of the sun not been deflecting that light from far away.
So Eddington's able to show that Einstein's general relativity theory is right, and a revolution in science has been accomplished.
In classical physics, light is described as bending when it passes near massive celestial bodies, an idea made famous by Einstein's theory of general relativity. However, this interpretation may be an illusion rooted in geometric assumptions rather than physical particle behavior. Light is particle-based, not curved. Light is composed of particles quanta that compress into a high-density stream, giving the appearance of a wave or beam. This dense stream can break apart under certain conditions, spreading out rather than curving. The apparent curvature is not due to space bending, but to light's interaction with gravitational fields. This idea can be traced back to the Michelson-Morley experiment, which demonstrated that light behaves as a particulate phenomenon independent of any etheric medium. The spreading of light near massive bodies is more accurately described as being diffusion caused by gravitational interference, not curvature. The misinterpretation of Einstein's geometry. Einstein's model relies on a two-dimensional representation of space as a malleable surface where gravity wells cause light to curve. But this geometric analogy may obscure the true 3D nature of space, in which light interacts with mass differently than simply bending. When light passes near a celestial body like the Sun, it doesn't bend around it. Instead, the dense photon stream is disrupted by the gravitational mass, causing a diffraction-like spread. This spreading creates the illusion of a curved path and ellipsogenetic effect without true curvature occurring. Implications for Earth and heat transfer. If light truly bent around celestial objects, Earth would experience different heating dynamics. The Sun's thermal energy, guided by its emitted light, would miss Earth entirely if light were genuinely curved away from a direct path. Thus, observational consistency in solar heating implies that light remains largely on a straight trajectory, modified only by dispersive interactions, not by spatial curvature. Quantum physics theory perspective. According to quantum physics theory, space is layered and volumetric, not a flat 2D field. Light as a particle phenomenon interacts with this layered structure in ways that can mimic wave behaviors and bending illusions, but in reality, it spreads due to field interactions and density gradients, not space-time curvature.